Okay, let me explain to you how to find we want to talk about Bernoulli, mostly how to get the mean, variance and moment generated function of Bernoulli distribution. As we know, Bernoulli distribution is a discrete probability distribution of a random variable which takes the value 1 with probability p, and you know p is probability of success, and the value 0 with probability q. Q is equivalent to 1 minus p, which is probability of failure. So which means S can either take the value 0 or 1. P is the probability of success, while Q is the probability of failure. That is just like Q is equals to 1 minus P. Okay. So the probability mass function of Bernoulli distribution is given as P of x, that is a probability raised to power s, Q raised to power 1 minus x, is 0 otherwise. So here now, s can either take the value 0 or 1. That's why we have it here. S can either take 0 or 1. Then this P is the probability of success, and we have Q here to be the probability of failure. And as you know, Q is the same thing as 1 minus P. So first of all, we want to look at the mean of a Bernoulli distribution. How to find the mean of a Bernoulli distribution. Mean of a distribution is given as E of x equals to summation x runs from 0 to 1, x multiplied by the probability mass function of the particular distribution. So P of x now is the probability mass function of the distribution we are looking for, that whereby E of x, that is when you multiply this by this probability mass function, we are going to have the mean of the distribution. Now, and as we know, P of x is the probability mass function of Bernoulli, which is P raised to power x multiplied by Q raised to power 1 minus x. We have 0 otherwise here, that is when the probability is not certain. Definitely we have 0. Now, if we open this, we are going to have a summation x run from 0 to 1, x multiplied by P raised to power x, Q raised to power 1 minus x, P raised to power 1 minus x. And we have summation here, which means x run from 0 to 1. The value of s is 0 and 1. So if we open this, that is substitute 0 and 1 into this summation, hence we are going to have the whole of this plus when s equals to 0, the whole of this when s equals to 1, and we're going to have this is 0 multiplied by P raised to power 0, Q raised to power 1 minus 0 plus 1 multiplied by P raised to power 1, Q raised to power 1 minus 1. Now we have a 0 here because we have x here. When we take x to be 0, so all of x here is equals to 0. That's why we substitute 0 here, plus when x equals to 1, and that is why you substitute x to be 1 here. Therefore, 0 multiplied by the whole of this equals to 0. Then we deal with this. 1 minus 1 here will give us a 0. Q raised to power 0 will definitely give us 1. That is 1 minus P raised to power 1. And we're going to have 0 plus P. 0 plus P will definitely give us P. So which means the mean of a Bernoulli distribution is P. So this is just how to derive the mean of the probability mass function of Bernoulli distribution. Now we look at variance of a Bernoulli distribution. How to derive the variance of a Bernoulli distribution. If you are trying to derive the variance of a distribution, if you are not using the moment generating function to derive it, definitely we have this formula, which is variance x equals to E of x raised to power 2 minus E of x all raised to power 2. Now, if you remember, E of x here is the mean of x. Is the mean of the distribution, which we've already gotten in the previous slide, and this is equals to P. So what we need to work on now is e of x raised to power 2. Therefore, we need to get the value of e of x raised to power 2 before getting the variance. Since we already know the value here, we already know what e of x is, then we need e of x squared of the distribution. So therefore, we have e of x squared equals to summation x runs from 0 to 1, x raised to power 2 multiplied by probability of x. The probability of x here still stands for the probability mass function of Bernoulli distribution. So when we multiply x raised to power 2 with this probability, when x runs from 0 to 1, therefore we're going to have this. That is summation x run from 0 to 1, x raised to power 2, p raised to power x, q raised to power 1 minus x. That is p of x, which is a mass function here. So if we substitute the value of x, which is 0 and 1, therefore we're going to have 0 raised to power 2 multiplied by p raised to power 0, q raised to power 1 minus 0, then plus 1 raised to power 2, multiplied by p raised to power 1, q raised to power 1 minus 1. Now, 0 raised to power 2 will still give us 0. Then 0 multiplied by the whole of this value will give us 0. Here we still have same thing here. 1 minus 1 will give us 0. Q raised to power 0 give us 1. Therefore, 1 multiplied by p times 1 will still give us p. Therefore, we have e of x squared to be equals to 0 plus p. And 0 plus p will definitely give us p. Now, remember, e of x in the previous slide give us p. Then e of x raised to power 2, that's expected square value of Bernoulli distribution, still give us p. Now we want to apply this formula. Let's remind us the formula is a variance of x equals to e of x raised to power 2 minus e of x s all raised to power 2. Now e of x raised to power 2, the value here is p, and e of x is p in the previous slide. So therefore we have something like this: p minus p raised to power 2, because here we have all raised to power 2 here. So we have p raised to power p minus p raised to power 2. If you collect the like time, we're going to have, that is p is common, that is a common factor. So we have a p into bracket 1 minus p. P into bracket 1 minus p. Remember, we have 1 minus p to be equals to q. So which means variance of s can be presented as p into bracket 1 minus p, or we present it as variance of s equals to pq, because 1 minus p is the same thing as q, which is the probability of failure. E of x, that is the mean of Bernoulli distribution, is p. Therefore, the variance of same distribution is equals to pq, that is the probability of success multiplied by the probability of failure. Now let's look at the moment derivative function of Bernoulli distribution. Moment derivative function of Bernoulli distribution. So more explicitly, the moment derivative function of s can be written as, we have a m subscript x of t equals to summation, you can say s raised to power tx multiplied by p of x equals to x dx. X is discrete. Because s is discrete, that's why we have this formula here for the moment derivative function of x. Since Bernoulli distribution is a discrete distribution, that's why we have this formula for it. And what does this translate? We have m subscript x of t equals to e of expected value of exponential tx, that's exponential t raised to power x. So what are we going to do? Summation all of these multiplied by the probability mass function of Bernoulli distribution. Then we have it as m subscript x of t equals to summation x run from 0 to 1 exponential tx multiplied by p raised to power x, q raised to power 1 minus x. That is, we multiply the the exponential function by the moment by the distribution of Bernoulli, and that is why we have p raised to power x, q raised to power 1 minus x. And as we know, s can only take two values, which is 0 and 1, and that is why x runs from 0 to 1. So if you substitute the value of x into this equation here. So we're going to have summation x run from 0, p raised to the power exponential t s q raised to the power 1 minus x. And what have you done here? This is exponential tx and we have p raised to the power x. So we have common power here, which is x. So we join these two together, that is p exponential t into bracket, then we have the common factor, which is x as the power outside, then we have q raised to the power 1 minus x. So now from here now we can now substitute the value of x, that is 0 and 1, into this equation. Therefore we have p exponential t raised to the power 0 q raised to the power 1 minus 0 plus p exponential t raised to the power 1 q raised to the power 1 minus 1. When x is 0 plus when x is 1, p exponential t raised to the power 0, that is all of this is going to be 1. All of this is going to be 1. 1 minus 0 is 1. So we have 1 multiplied by q raised to the power 1 will still give us q. So we have q here. Then here 1 minus 1 is 0. This is 1 already. P exponential t multiplied by 1 will still give us p exponential t. So here now we have a q plus p exponential t. So we have equals to q plus p exponential t. So this is the moment generated function of a Bernoulli distribution, or better still, we'll write it this way: m subscript s of t equals to p exponential t plus q. So that is the moment generated function of exponential distribution. So we have the mean to be p, the variance of the same distribution to be pq, whereby the moment generated function of the distribution is p exponential t plus q. So this is simply how to derive the mean, variance, and moment generated function of exponential distribution. Although the case can be reversed, whereby we can also derive the mean and variance of this Bernoulli distribution from its moment generated function. And how do we do that? We simply differentiate. For the mean, we differentiate, that is the first difference level, whereby for the variance, that is the second order, that is the second difference level. So this is just how to derive the mean, variance, and the moment generated function of